Hello everyone, this is Sri Banerjee, and here with me is my colleague Matt Jones. Drawing from our experiences and expertise as faculty members in the areas of public health, statistics, and public policy at Walden University, we will be presenting on a novel comparison of modeling cancer data based on ordinary least squares versus geographically weighted regression. Matt will be presenting the first half of the presentation, while I will be covering the second half.
Our objective today is to really understand how model choice potentially impacts health policy, especially when dealing with spatial correlation with the data. And to do this, we're going to compare an OLS regression model with a geographically weighted regression model. And just as a reminder, here is the abstract. I know there's a lot of words there to put up on a screen, so I'm certainly not going to reread this to you, but I'll give you a second to glance over it. As I mentioned earlier, we're going to be constructing an OLS model, a fairly basic model, just for the purposes of our demonstration here, with our dependent variable being the age-adjusted breast cancer incidence rate with cases per 100,000, and two independent variables that from the literature have shown to be fairly strong or important predictors of this dependent variable, and that's the poverty rate in percentage and the Gini index, which is a measure of income inequality. Now, I'm sure many have seen the Gini index before, perhaps have previously used it in their own research or at least seen it in the literature before. But for the sake of some summary, the Gini index is a summary measure of income inequality where the coefficient ranges from 0 to 1, where 0 indicates perfect equality where everyone's receiving an equal share, and the value of 1 reflects perfect inequality. And we just wanted to acknowledge that there are several other potential modeling strategies here for this data, and that on its face, ordinary least squares regression might not be the best approach. There are these other approaches that might suit the count data, the source of the original data being count data, a little better. But for our purposes here of comparing the geographically weighted regression model, we're just going to compare that to the ordinary least squares regression. And here we have the results of our OLS regression model without any spatial lag. So this is the very basic modeling approach. And you can see here that all of our predictors, both the predictors, are significant predictors of our outcome variable. And specifically what we're going to be looking at here in just a second when we move to our geographically weighted regression model is that adjusted R-square value to look at model summary. And here you can see that although this explains some of the variance, it perhaps isn't the best model with these two predictors.
We will be going over geographically weighted regression in a moment, but before we do so, we wanted to briefly show you how a Poisson model would look like. Here are the model specifics for a Poisson model of Gini index and poverty rate versus breast cancer index. While the Poisson model can be better suited for count variable on cancer, we will still be using the original OLS regression model that we constructed in order to compare the geographically weighted regression. Traditionally, the geographically weighted regression model was built as a complementary approach to OLS regression. In the next two slides, I will be going over key concepts in constructing a geographically weighted regression model: spatial autocorrelation and spatial non-stationarity. If you measure something over space, for example, poverty rate, it is likely that two observations that are close to each other in space are also similar in measurement. Translating this to our scenario, poverty rate in neighboring counties is more likely to be similar in measurement. This assumption is also known as the first law of geography. Everything is related to everything else, but near things are more related than distant things. Spatial non-stationarity is a condition in which a simple global model cannot explain the relationships between some sets of variables. The nature of the model must alter over space to reflect the structure within the data. For example, you're trying to model the relationship between two variables. Say, for instance, number of cars per person and income in a given city. Using a global linear regression, you find that neighborhoods with higher incomes have more cars per person. However, in some neighborhoods where public transport is better, this relationship changes. And even with a higher average income, people tend to use public transportation. Spatial data often do not fit traditional non-spatial regression requirements because they are spatially autocorrelated. As I said earlier, features near each other are more similar than those further away. Non-stationarity, features behave differently based on their location and regional variation. And it's important to note that no spatial regression method is effective for both characteristics. The geographically weighted regression, however, is a technique mainly intended to indicate where non-stationarity is taking place on the map. That is, where locally weighted regression coefficients move away from their global values. Moran's I is a standard measure for spatial autocorrelation. This measure evaluates whether the pattern expressed is clustered, dispersed, or random. When the p-value indicates statistical significance, as seen in the case of breast cancer incidence rate above, a positive Moran's I index value indicates tendency towards clustering, while a negative Moran's I index value indicates tendency towards dispersion. This illustration of spatial autocorrelation is a bit more detailed than what was in the previous slide. Again, as a reminder, a value of -1 is considered perfect clustering of dissimilar values. You can also think of this as perfect dispersion. A value of 0 is no autocorrelation or perfect randomness, and a value of +1 indicates perfect clustering of similar values. It's the opposite of dispersion. Given this information, we will be using the concept of spatial lag as well. As you can see, the x-axis is spatial lag. From these graphs, you can see that spatial autocorrelation is indeed taking place. From the Moran's I, we can see that clustering takes place in the lower spatial lag values. As expected, as the lags increase, the Moran's I value starts to decrease. On the right-hand side, we assess for spatial autocorrelation of the residuals. Spatial autocorrelation in the residuals is often interpreted to mean that an important independent value is missing from the regression, or an underlying spatial process that induces spatial autocorrelation in some of the variables is missing from the model. We now must investigate further the spatial process through the non-stationarity principle in a geographically weighted regression model. We had the option of using the modeling strategy of either a spatially lagged dependent variable or spatially lagged independent variables. While many spatial software use by default spatially lagged dependent variables, as has been pointed out by previous researchers, spatially lagged independent variables can provide further insights about geographical weighting when using social influences. This has been established in the equations provided at the very top of the slide. As we can see in the table at the bottom half of the slide, the model coefficients demonstrate that the spatially lagged Gini coefficient variable and poverty rate variable are both statistically significant. However, even more importantly, when we compare the R-squared between Ols regression and geographically weighted regression, the geographically weighted model performs more superiorly than OLS regression. So what are the key findings? Gini coefficient and poverty rate significantly predicted age-adjusted breast cancer incident rates per 100,000. The results of OLS regression indicated the two predictors explained only 17% of the variance. However, when geographically weighted regression was applied, the four predictors explained 23% of the variance, clearly making this a better model fit. Spatial autocorrelation tests established that geographical considerations were necessary in our final model. Additionally, geographical weighting is important when considering cancer-related characteristics, such as in thyroid cancer, colon cancer, lung cancer, and
So our goal here was to show, using some basic models, how spatial correlation can impact policy somehow, and not accounting for that spatial autocorrelation can bias our estimates. Therefore, we might not be able to fully understand the possible implications of spatial dependence, especially when we're looking for a better understanding of disease prevalence and its correlates. So this in turn really provides policymakers and health educators with a more accurate understanding of their populations and risk factors. Therefore, obviously, it's important to choose the best modeling approach that we can. And this will give us a more targeted and effective approach to mitigating some of the effects of this disease prevalence. And additionally, from a policy standpoint, these spatial models can really help us incorporate the effects of inequality that are associated with quote unquote place, i.e. your zip code.
here are our references. Thank you so much for listening to the presentation.